Hello everyone, welcome back to another Mathematics and GIS lecture video. And in this lecture video, what I want to do is I want to go through an example of how we can get an equation for an equal area cylindrical normal projection. And what I mean here is if you think back to our previous video where we went through the idea of an equidistant projection, where we assumed that this equation here was true, right, that we held the northing to be equal to the radius of our reference globe times the latitude, and we assumed that the easting was equal to the radius of our reference globe times our longitude. That because of the key properties of the reference globe, that our northing was actually always going to be correct, right? Because that the distance along a meridian would always be true, but yet if you remember that the meridians were supposed to converge at the poles, right, which means that the distance between the meridians would actually shrink the farther north or farther south you go. We're not accounting for that here. So the distance east-west would have actually been incorrect. And so if you think about area, right, area usually involves some combination of multiplying by a length and a width, that one of them was going to be right, in this case the north-south, but the east-west was going to be wrong. So our area, or any area that we calculated, would be wrong. So hopefully that makes sense. So what we need to think about now is how do we go about making a difference projection equation that would assume that this is true, right? That we're going to call this true, even though it's not. We're going to then alter our northing here to account for that difference. We're essentially going to squish or stretch the northing so that the ratio between these two is right, so that when we calculate the area, we get the right area. I know that probably didn't make a whole ton of sense. Hopefully when we walk through getting to the equation, it will. And when we go through some examples at the end of this module and we see how things look, it will make even more sense. So let's talk about what we know to be true here. We know that right now our easting, the way we calculated it before, was equal to the radius of the reference globe times the longitude of the point. But if we think back to our triangle that we made here, right, we know that what it really should be, right, if we were to squeeze this down infinitesimally small so that we can apply differential and integral calculus to these things, we know that what we really want it to be would be r times cosine of the latitude, right, times longitude. So what we've done here is we've actually messed this up by a factor of cosine longitude. Or sorry, cosine latitude, right? The difference between this equation and this equation is cosine latitude. So what we can do to fix that problem is we can introduce this idea of cosine latitude into the northing, and then we can integrate that function. And so this is going to look a little weird, and if you don't understand what's happening, it's okay. I really just want you to see where we're going to go from here to having a corrected northing that would be equal area. Okay? So what we can say is we can say the northing, right, should really be equal to the integral. Right? So this sign right here, this is the integration sign. And again, if you're not familiar with integral calculus, that's really okay. I'm just trying to walk through all of the steps so that you can see where things are coming from and where they're going. Right? We have our r, we have our theta, right? These are coming from this first equation here. But then we're going to insert here in this the cosine of theta. Right? So if we integrate this, again, I'm not expecting you to follow this step. Right? If we integrate this, right, the cosine theta integrated at theta, right, d theta, right, the integral of this d theta is going to give us a northing of r times the sine of theta. Okay. So our easting is going to be kept the same. Our easting is still going to be r lambda. So now what we've done is we've essentially compressed or stretched the northing so that the ratio of the northing and the easting makes it so that our area is preserved. Hopefully that makes sense. Again, if you have any questions, just kind of remember these equations right here. That for an equal area cylindrical normal projection, our northing is r sine theta and our easting is r lambda. Hopefully that makes sense. And as always, please reach out. Thank you.